Chapter 13 for AP Chem Review on chemical kinetics. Kinetics is referring to the rate of the reaction. Now let's say, for example, we're given the generic reaction of stoichiometric coefficient A of molecule A plus B equals C and D. The rate would be written as the concentration change over the change in time. Now notice the reactants, the A and the B, also have a negative sign in front of it because reactant concentration is going to decrease over time. Product concentration is going to increase over time. So the negative sign really means nothing other than to make sure that the signs equal out if I wanted to compare the change in concentration of A to B or C or D. So it allows us to compare all of those within that equation. Rate law and the order of the reaction is the next thing we have to refer to. The rate law is expressed as K, which is a constant, A to the X, B to the Y. Now the X and the Y is referring to the order of the reaction, which we'll talk about here in a second, and then again the A concentration, B concentration. There's 0 first and second order reactions that we are aware of, but unlike in the fall semester, we won't need to know the equations. So we went over all the equations for half-life and just any time within a reaction for first order, second order, and 0 order. We just have to know how to identify what order a reaction is. Now, there's two ways we can identify what the order of the reaction is. It's by either graphs or by looking at data. The first set of graphs is for first order reactions. So first order reaction, what we normally look at is the natural log of concentration versus time. If that is a straight slope, that's a good indicator that that's going to be first order reaction. That slope, by the way, you take the negative value of that, that's the K that you would use in the rate law that I showed previously. Notice that just the concentration per time is going to be this curve that will level off over time. Now on the bottom here is going to be the 0 order reactions. Now concentration per time is already a straight line for a 0 order reaction. Remember that in first order it had to take the natural log to make that occur. The natural log per time graph is kind of a goofy one right here. I was unable to find a second order graph online, so probably most likely is to know first order, it's the natural log versus time, that's the straight line slope for K. For 0 order, it's going to be just the concentration versus time graph. Here's an equation for us to look at next. Is something that we saw in the test of there's an equation, C2H4 plus O3 making H2CO plus H2CO2, and then I give you experimental data. There's 3 different trials. So trial 1, trial 2, trial 3 of concentrations and rate. What you want to do is figure out the order of the reaction by looking at this. For example, in experiments 1 and 2, the C2H4 concentration stays the same. The concentration of O3 doubles, 2.5 10 to the 8th, 5.0 10 to the 8th. So if the O3 doubled, what happened to the rate of the reaction? It doubled as well. So if this concentration doubles and the rate doubles, that's what's referred to as first order. It's kind of a direct relationship between the concentration of O3 and the rate of the reaction. Now let's look at 2 trials where the O3 stays the same. Trial 1 and trial 3, the O3 concentration stays the same. What happens to C2H4 in trials 1 and 3? You go from 5.0 times 10 to the 8th to 1.0 times 10 to the 7th. So this concentration doubles. Let's look at the rate. The rate goes from 1.51 to 6.02. That quadrupled the rate. So if C2H4 doubled in concentration, causing the rate to quadruple, that would be a second order reaction. Now if we were to write out the rate law then, I'll show that to you on the board here, the rate of this reaction would equal K, the concentration of C2H4, which remember C2H4, when it doubled, the rate quadrupled, meaning it's second order, times the O3 concentration, which would be to the first order. So this is how you need to use it. Either by looking at a graph or looking at a data table, you can determine the rate law, which the order is by looking at the data. Here's the concentration of the reactants to begin with. Next thing you need to know about is activation energy. Activation energy is referred to as the minimum amount of energy required to initiate a chemical reaction. There are 2 different graphs you can see here. One is endothermic and one is exothermic. The endothermic graph is right here. Reactants have a certain amount of energy. Then you have to climb up and get to this peak, which will be referred to as an activated complex. We'll talk about that in a little bit. And then the products have a new energy. Notice that going from here to here, you had to put a net energy in of letter C. Putting energy in is endothermic. On the other hand, right here is your reactants to begin with, going up above the curve for the activation energy. Products are down below. Here, there's energy given off. The reactants had more energy than the products. Energy can be released. That is an exothermic graph. Either way, they both involve getting over this hump to begin with of an activation energy in order for things to break apart and then reform. Continuing on with activation energy, you have what's referred to as an activated complex or a transition state. Not certain if you need to know all this or not, but we're going to give you an example anyways. Here is nitrogen monoxide plus oxygen to make nitrogen dioxide. The first step is going to be two of the NOs are going to react with each other to make what's referred to as an activated complex, the N2O2. The second step is that N2O2 is going to react with the oxygen to make the final product. So again, uncertain if you need to know whether or not this is important, we would refer to the N2O2 though as an intermediate. It's a product of the first reaction, a reactant in the second reaction. The reaction mechanism is the next thing to bring up. Reaction mechanism, intermediates, like I just mentioned, appear in the mechanism, but not in the overall balanced equation. The rate determining step of a reaction is the slowest step in which a sequence of steps leading to the product formation can occur. If I actually go back to the previous slide here for a second, if I had two steps, one might be the slow step, one is the fast step. So if we ask you what is the rate determining step, it's always the slower of the two steps. And I just made up step number one being the slow step in this case. So again, that would be the rate determining step. Moving on to a catalyst. A catalyst is a substance that increases the rate of reaction, sorry for the typo there, by lowering activation energy. So if this is our activation energy graph, initially this was the amount of energy that the reactants had to overcome in order to form products. What a catalyst will do is lower that activation energy. Now it's a smaller amount. Reaction can go faster because it does not have to obtain as much energy as it normally would. So again, a lowering of the activation curve is what a catalyst will do. Now, there are different catalyst types. Homogeneous means it's the same phase as whatever it's reacting with. Heterogeneous is it's a different phase. So usually a solid within a liquid or a gas. For example, we use manganese dioxide solid powder with hydrogen peroxide as a catalyst. An enzyme is a substrate-specific catalyst. And we're going to mention here to wrap up this slide the decomposition of hydrogen peroxide in the presence of Ki. So the very last slide we have to go over this. Here is the general equation. Now typically, if you wrote out the balanced equation of decomposition of hydrogen peroxide and Ki, your equation would be 2H2O2 yields 2H2O plus O2. You write the catalyst directly above the arrow then to show that it's involved in the reaction, but not completely because it won't get used up. Now the first step in that process is one hydrogen peroxide reacting with the I- ion to make water in IO-. Second step is the second hydrogen peroxide is going to react with the IO- to make a second water, O2, and the I- replenishes itself. So we could look at this reaction as well and identify a catalyst starts off the reaction and is a product at the very end. So it doesn't get used up. It's there at the beginning, it's there at the end. It just helps the reaction move on. And we talk about lowering the activation energy. The activation energy is lower because this complex here requires less energy to break up than just H2O2 on its own. Last thing to mention, back to intermediates, a product of the first reaction, IO-, is a reactant in the second. That is going to be an intermediate of that reaction. And that wraps up chapter 13 on chemical kinetics.